Okay, so today I'm going to be explaining free body diagrams. So right now I have this cologne just laying on this desk. So right now there's a force of gravity acting on this cologne. So this is our object, the cologne. And this is the force of gravity acting on it right now, which we can label Fg. But there's also a force acting on the cologne from the desk. This is to keep it from falling down. So we can label that this. And that force that's keeping the cologne at the surface is here is called a normal force, which we can label Fn. So right now, based off the free body diagram, we can see that it's at equilibrium, which means it's not moving in either direction. But if I were to make a different free body diagram, like this one, this would have to mean that the object's moving downwards, since the force normal is not enough to counteract the force of gravity. But there can also be forces acting in the x direction, such as this. We can call that a force applied. So you have force normal, force of gravity, and then you also have your force applied acting in this direction, because my finger is applying the force. So based off this free body diagram, we can see that in the y direction, which is up and down, it's not moving, but in the x direction, it's moving to the left. But when I move it, there's also another force acting against it. This is called force of friction. So whenever I move it, there's friction between the surface and the cologne. But based off this free body diagram, we can see that the force applied is greater than the force of friction. So that must mean that even with the force of friction, it's still moving this way. But if I were to increase the force of friction to make it equal, then we would be able to see that it wouldn't move, because the force of friction is able to counteract the force applied. And then there's also a thing such as a tension force. So if I were to lift this up and pretend that my hand was a rope, we could call this force of tension. So the free body diagram for this would be this. So that's our object. This is the force of gravity. Then obviously when I had it up here, it's not moving, so there must be a force counteracting the force of gravity, and that would be the force of tension, which we can label as this. So based off this, we can see that it's in equilibrium. But let's say if the force of tension was greater in the free body diagram, so like this would tell us that the object would be moving upwards, like this, since the force of gravity wouldn't be able to counteract the force of tension. And then it can also be on a ramp. So if it's on a ramp, it's at equilibrium, right? So we have our object on the ramp. Oh, I messed that up. Okay. So that's our object, and then this is the ramp. So right now, the free body diagram for this would be this. The force of gravity it still points downwards, but since it's at an angle now, there's also an x component of gravity acting on this object. So obviously this free body diagram would mean that it wouldn't be at equilibrium since the forces aren't balanced. So there has to be a force normal to counteract the force of gravity. So, oh, that's sloppy. So we have force normal acting in the y direction to counteract this. But there's also a force of gravity acting in the x direction. So that must mean that there's a force of friction going the opposite way to keep it at equilibrium, like this. So we can do this here.